So while ordering some other stuff on eBay, I just saw this lamp and decided to throw it into the mix, and it's a standard sort of, well, I mean, they are a standard thing these days, a lamp with a passive infrared detector built into it. And this one came from an eBay seller called, oh God, Mandy, M-A-N-D-Y, X-I-A-O, 2011. Mandy Zayo 2011. That's not easy to remember. I'm guessing that they have to just invent these big long names because, you know, there are so many names taken with eBay that it must be quite hard finding, you know, one that's not been taken already. So this is supposedly a 5-watt LED lamp. It says 110 to 220 volt. And it's got 18 LEDs, it does have 18 LEDs, I've counted them. And it is, you get the choice of cold white or warm white. And the construction is interesting because it pops open quite easily. And once you've opened it, you've got what looks like a passive infrared module in the end, a LED circuit board, and then a power supply. Now, this surprised me. I was expecting this to be the typical, I'm looking around for one and not seeing one, as is so often the case, one of the little tiny switch mode power supplies that you often find in the 3-watt lamps. And instead, it looks like it's 2 capacitive droppers and what looks like an Opto Isolator in the middle. So I'm guessing that one capacitive dropper is for powering the passive infrared detector and the other one is for powering the LED lamp. It's the first time I've seen this, and you know what that means? It means I'm going to have to take it completely to bits and reverse engineer it. So I shall go and do that right now. Well, I have to say this is extremely modular. It's quite appealing for that aspect. It's got the passive infrared module that plugs into the end of the main power card. It's got the power card that plugs into the LED card, and yeah, it's very modular. It comes into 6 distinct bits. So taking a look at this. This is quite interesting because this circuit board actually contains 2 distinct modules. One module is the power supply for driving the passive infrared module, and the other section is the power supply for driving the LEDs, and it's switched by an opto triac and an auxiliary triac, which is a bit odd. So looking at the circuitry, the first section for the passive infrared detector, it's the top section of the circuit board here, has a 100 ohm resistor which acts as a, I suppose, I would say not an electronic fuse, but a fusible type resistor. The metal film tend to fail in a more controlled manner than the carbon film ones, which just burst into flames. But it's also, the 100 ohm value suggests it's also acting as a sort of inrush limiter to help try and take transients away to protect the circuitry. So it's got a 560 nanofarad 400 volt capacitor, and that is quite a high value. I think this module is used for 120 volt lamps as well as 240 volt lamps, and they've just standardized. And there's other characteristics of this circuit board that make me think that. So the capacitor basically acts as a sort of current limiter. It lets a portion of energy through in each half of the sine wave, and it's got a 1 megohm discharge resistor across it, which is good. And then it's got a Zener diode, and the Zener diode is here. It's rated about 19 volts, and what that does is a Zener diode has a very precise reverse voltage that it basically caps the voltage at 19 volts. And there's also, normally I'd expect, after this, I'd normally expect to see a diode in that position, but they've actually put it down there. And initially it was a bit odd to see it down there. It works fine that it's down there. It means that this rail here, the negative rail, is just a wee bit raised above that voltage rail, but it doesn't really matter. And the only reason I can think of them doing that is because by putting the diode over here, they've effectively made it double up as a diode and a link. It's jumped over 2 other tracks, and it may have just made the circuit board design easier moving it to that position. So what you end up with across this 100 megafarad 35 volt capacitor is a supply of 19 volts, roughly. Quite a rough supply, I have to say. It's not an ideal, you know, it's a sort of half-wave supply, but it's good enough because that's quite a low current module. And that goes out via this 3-pin connector. It's got plus volts, the plus 19 volts, the negative volts or 0 volts, and the switch signal back. The switch signal back goes through a resistor and then an LED in an Opto Isolator, which is buried right in the middle. and that's used to control the other side of the circuitry. Quite odd what they've actually done here. The PIR module has one oddity to it. This is the schematic from the manufacturer's website of that PIR control chip, which is an EG4002. Possibly the first time I've come across one of those. And it differs. I'm just going to nudge the intensity down a wee bit here just to make it a better contrast. They've added one other thing to try and make the power just a wee bit smoother. This is a 3.3 volt regulator. They've also added in line a 78L12, a 12 volt regulator. So that drops the 19 volts down to 12 volts, and then it then drops down to 3 volts again. That just adds an extra layer of regulation. It probably makes it more stable, because these chips tend to require a very stable supply voltage, because otherwise they can be prone to false triggering. What's really odd about this schematic here is that it actually shows the whole pyroelectric sensor module. Now, pyroelectric sensor modules, this little metal can at the end here, they've got a window that lets through infrared energy. That it can see you almost like, what was that film, Predator, where you can see the sort of thermal imaging camera effect. That's what it sees, but it sees that sort of wavelength of energy. And it's got two pyroelectric sensors that create a very small voltage. They're like solar panels, but they respond specifically to that wavelength of infrared energy. And they're connected in reverse parallel. And the lenses, and that's where this little assembly comes in, this polythene lens that clips over the front of that. That's where it comes in. It creates distinct patterns. As you walk past it, it needs these ripples because it creates sort of a push-pull effect. It suddenly causes sharp transitions in these, and that results in voltage fluctuations which are then buffered inside this little metal can by this transistor. And the reason they buffer it locally is to avoid having long tracks. It makes sense. It's like an electret microphone. It means that the tiny signals in there get buffered up, so you end up with quite a robust signal coming out. It's much less chance of getting interfered with by just random electrical interference, because it's all in the screened can. So all you have to do is supply that device with the 3.3 volts from this regulator, and the negative rail, or the 0 volt reference, what they call ground, but it's not actually mains ground. That's the wee earth symbol there, which, you see this a lot in schematics, but where main circuitry like this is involved, it doesn't actually mean earth or ground. It just means that the local ground reference to this circuit. And if you touch this, you probably would get a shock off at the ground in here, because it's not actually, the ground we are used to. So the output of that fluctuates when someone walks in front of it. It fluctuates slightly, and this capacitor here blocks DC. All it will do is charge up to a specific level, but it won't let an it won't let a flat DC signal through. It will just charge, and that'll be it. However, the fluctuation passes through the capacitor. It causes a slight charge transfer from either side, and that then goes in here. And this is very clearly an amplifier, and I've downloaded the rest of the data sheet off this site. Note that the data sheet is unfortunately completely in Chinese, and although Google can translate these data sheets, it can't relate it all to the pictures. It certainly can't fill in the text in these yet. That may happen in the future. But it's nice to know that I can look at this and it doesn't, it doesn't even register the fact it's Chinese. I just look at the schematic and I can read it. It's just the way it works. And it shows, it's a very simple chip, I have to say. For passive infrared detectors, it's very, very simple. It's got the input here, and it's got an op-amp, which is got a voltage reference supplied to it. They've got a couple of voltage references inside that are just derived from the supply voltage. And the output is fed back to the negative input, the inverting input, and to keep things simple, that just means that this turns it into a very high gain amplifier, and that slight ripple when you walk in front of the sensor causes a much greater fluctuation here, which then gets buffered again. And this probably is just a buffer, an analog buffer, and then it goes to two comparators, each with another voltage reference, so that if it exceeds 0.5 volts or drops below 0.1 volts, it triggers the output. And that goes through an OR gate, which combines the two. It's either one or the other will trigger it, and is combined again with an AND gate, which an AND gate only triggers if both the first and the second input. That's why it's called AND. The OR is called an OR gate because either of the inputs, one or the other, will trigger the output. And the AND gate means that both the inputs have to be high to trigger the output, so to speak. You know, input A and input B, and that's tied to VC, the VC input, which is the light sensor. I'll show you that on the circuit board. This is the LDR, the light sensor resistor here, and that basically enables the output if it's dark enough. And once it's got the two conditions are met, that it's dark enough and it's detected movement, it will trigger this. And that's where this differs greatly from the standard chip we're pretty much used to in most passive infrared detectors, the BISS 0001. This one has a built-in oscillator and some sort of timing logic built in here. And that oscillator is based around this 1 nanofarad capacitor and this 300k resistor. And it will just be basically charging and discharging that capacitor, and to provide the timing reference. And that then must control the output for that time delay that you'll set probably by the choice of those components. And it's interesting that the output of this has a diode that then goes to the light sensor input, which means that when this is triggered and when it's actually switching the light on, it effectively overrides the light sensor. And I guess that means that you know, if you keep moving about under it, it's not, if it could see the light sensor, when it's lit up, it'll obviously be swamping that light sensor because it's in the same package. But so it would appear that it was daylight and it would want to turn the light off. But by overriding that with that diode, it means that if you're moving about underneath, it will just keep triggering and triggering. And I'm guessing that might be what this function, this pin here is for, to choose the mode, whether it's it can be re-triggered or it has to wait until it's cleared. In an alarm situation, it would wait until it was cleared, but in a case like this where you wanted to keep triggering the light and keep it on while you're moving about under it, that, I'm guessing that's what that chooses, the re-triggering function. I don't see the diode on this. I wish I'd checked that now. I'll check it, I'll put this back together afterwards and I'll probably check that then. But the diode is the difference between this unit going off every time after the time delay and then having to be re-triggered, or just re-triggering and not going off at all as long as there's movement detected. Very neat, very simple chip. It's a very minimalist layout. You can see the two regulators here. The first regulator is the 12 volt regulator, and then the 3.3 volt regulator, and then just a few support chips. Then this transistor. Now there's another variation from this circuit here. This one uses a 1K resistor to drive, actually, I'm just going to double check that now, just in case I'm talking crap. No, it's 102. 1000, it's using a 1000 ohm resistor instead of a 10K resistor to drive this transistor. And this transistor is then providing that signal back to this module to turn on that Opto Isolator. So let's move back over to that schematic. Now that I've completely digressed completely. It's quite a neat arrangement. It's quite a neat little chip, that. It's definitely one of the more modern type chips. So, there's the PIR module, and you've walked in front of it, it's triggered, and it's turned the output on, and is pulling that LED down to ground via the resistor, and it's lighting the LED. Oddly, they're using a Opto Isolator called an EL... now, where is that? I thought I had some more information on that, and I've just completely misplaced it. I thought I did have more information. Oh, there it is. This is what I used to reverse engineer it. I basically took a picture of the back of this and then flipped it so that I can actually transfer the components directly on, you know, in exactly the same sort of positioning, so that there's the connector there, there's the pins for it. It uses a 3061 Opto-Triac. Now, the Opto Isolated track is a device that can switch the AC side when you basically, all you have to do is power an LED in one side and it completely isolates the two sides, and it lets you switch on, in this case, the entire circuit here for driving the LEDs. And it seems a bit odd. If you work it out, that's switching from, I think that's switching from the 19 volt rail, hold on, let me think, 19 volts minus about 19 volts minus about, say, 1.5 for the LED, as it often is inside these opto isolators, divided by 2,200 ohms. That's about 8 milliamps, which is really odd, because the opto isolator they've used requires 15 milliamp trigger, but they're probably just, yeah, I'm not sure why they've done that. They do another version of the opto isolator that is more sensitive. I think it's the 3062. It's a generic. You know, the lots of different manufacturers make this, like MC3061 or just 3061. It's one of these components that is so common that it's just become a number, 3061, but it's loads of manufacturers make it. But looking back at the circuit here, this is like a sort of slightly disjointed LED lamp circuit, in the sense that here's the capacitive dropper again. They're using 1 microfarad at 400 volts, that's this component here, and they've got a discharge resistor across it. And normally, if it was just an ordinary light, that would just feed a bridge rectifier, maybe a smoothing capacitor, and then the LEDs. But they've broken it down into the two circuit boards here, and it's quite odd. There's a 4-pin connection going between them. I would have thought that it would just be a 2-pin connection, but they've actually mounted the capacitor, the smoothing capacitor, back off this board. The AC goes onto this board and gets rectified, and then it comes back off another 2 pins just to that capacitor there, and then back onto the board. You know, that just acts as a smoothing. I'm not sure why they didn't just put that capacitor on the board. It may have been for heat reasons, which would make sense. Okay, so here's the opto isolator. It's basically the opto isolated track here. And then they've got another track, BT131, which is a very common track. Now here's the oddity again. They could have just switched this lamp circuit board, because it's only going to be 20, 30, 50 milliamps. This opto track in here, and it's right in the middle, I don't even know if you'll see that, it's buried right between these and I can't bend these back too much. But there's a little 6-pin opto track in here, and it could theoretically have driven that panel no problem. And that's another thing that makes me think that maybe this is designed for a wider range of lamps, because maybe they've used the secondary track so they can not just use this one, which is a slightly higher current rating than the opto isolated track, but they could also make that even bigger. They could switch quite large circuits of LEDs with it. But as it is, they've used this opto track to drive a bigger track, which then switches the power on this circuit board to the bridge rectifier, which is made of 4 discrete diodes, gets smoothed back off the board, and then has a 470k discharge resistor. That's that tiny little resistor there. And these are just ordinary LEDs. It's not the multi-chip LEDs. These are just individual chip LEDs. And I tested that simply by putting this round to continuity and then applying it across one of the LEDs. And I'm not sure if you'll see that. I doubt you'll see it. Yeah, you can see it if I cover it like that. That I can make that one LED light, which means it is just a single LED chip, because if it was multi-chip, the meter wouldn't put out enough voltage to actually do that. So, yeah, very odd. It's neat. I like it. I like the fact it's really modular. And it looks like it is designed to be made for different voltages. It's designed for different arrays of LEDs, and I'm guessing that the reason that capacitor's down there is partly for thermal reasons, because that would make sense. As it is, it's one of these circuit boards that's sort of like a radial segmented section. It's mostly copper. It's not got the aluminium core, but it is mainly a large array of copper, with the LEDs soldered across each segment for maximum thermal dissipation. So it's a neat lamp. you know, it seems really good quality. The price of it was low for what's in here. It seems nice. And that's fundamentally it. So now I'm going to put it back together. Now I've actually realised about that diode thing that's not been implemented. I wonder, I'm going to put it back together and see if that will continually re-trigger, which means dancing about underneath the light in the dark. But yeah, interesting. It's very neat. So I've now put it back together and danced about under it in the dark. Okay, so it has a 30-second time delay, which is obviously set by those component values in the schematic. Grabs the schematic. These two component values. And unfortunately, I timed it for just about 30 seconds, then ran backwards and forwards underneath it to see if it would re-trigger and just continue staying lit. No, it goes out and has to re-trigger. One freaking diode would have fixed that. That's quite annoying. That means this is not suitable for use in the bathroom, because if you go in for a quick slash in the middle of the night, it's going to turn off while you're in the middle of your slash, and it's not going to turn on again until you've jumped about, probably spilling quite a lot of urine on the floor in the process. Oh, that didn't go in the direction I intended. Not to worry, that's what you expect on this channel. So this is currently drawing about 0.3, 0.4 watts standby, which is pretty low. And the current it's drawing at 245 volts is 42 milliamps. Again, if you do the maths, that's just going to look nonsensical, but that's the very basis of capacitive droppers and power factor, and yeah, it's complicated. If you do a search for power factor on the internet, it's not good. Not even with a good thorough drink beforehand, it's not a good subject. But basically it's to do with voltage and current and how they are synchronized, and it just seems to defy the laws of common sense and happy, fun electronic crap. So here we have the lamp, and I'm going to trigger it now. So let's put it back to the mode where it's dark, and I'm going to have to tuck it right out of sight to make this trigger and cover it over. So it's popped up to, the lamp's actually drawing about 3.5 watts itself once it's lit. It's a nice warm white. I chose warm white. They had them in warm and cold, which is nice. It seems okay. It puts out a modest amount of light. The current is going to be huge now, probably. It's 111 milliamps, which if you do the maths on 245 volts would theoretically make it 245 volts, P equals IV. So 245 volts times, that was about 111 milliamps, 0.11, yeah, 111, equals, that would make it 27 watts, except for the power factor thing, which makes it just 3 or 4 watts. So, yeah. Now, this also made me wonder, do other countries, I think, was it someone in Italy mentioned that their electricity meters measured the power factor as well? I mean, modern smart meters can measure power factor versus the older meters, but I wonder if they actually charge for that as opposed to real power that's actually used. That would be very annoying if they did. That would suddenly mean in some countries, if they charged for, you know, apparent power, that would mean you'd be paying a lot more to run your LED lamp than the electricity it was using. But yeah, so that's a slight annoying feature. I wonder if I can open it up and stick that diode in. Quite annoying actually that it does that. Oh, this also comes apart very easily. I think I mentioned that earlier. It's just the way it's put together. Yeah, I'm just thinking, you know, I'm very tempted to stick that diode in, but I don't know how well it would work. I suppose there's only one way to find out. One moment, please. Yep. That fixed it. I mean, why did they not include that? All I did here was add a diode pointing from pin 6 to pin 3. I mean, really, I just stuck the diode across the pins 3 and 6 of the chip. And, I mean, that's the diode there, going from pin 6, pointing towards pin 3, and suddenly, yeah, it re-triggers, so that, you know, as soon as I can walk about the room for, you know, any length of time I like, and it will turn off 30 seconds after I've not triggered it. So, why didn't they do that? That seems strange. But yeah, that's just suddenly improved it greatly. Yeah. So, an interesting light. It's really nice, it's modular, it's hackable apparently. So, yeah, it's a neat lamp.